I would like to begin by thanking the organizers for inviting to speak in this exciting workshop. I will be talking about robust optimization and its applications to machine learning. Adversarial robustness is a topic that has been gathering a lot of interest in machine learning these days. In operations research, particularly in optimization under uncertainty, robustness to adversarial perturbations is a topic that has kind of have always been of interest because of the following problem. So a typical problem in optimization to minimize a loss or maximize expected utility with respect to a given probability distribution. Usually you calibrate these probability distributions from data. Here we have an example of mean variance portfolio optimization where we have a portfolio of 100 assets which is optimal for a particular mean and variance configuration. So what has been known for a while is even a small perturbation like a 3% change to the mean of one asset is enough to drive out around 25% of the assets of the optimal portfolio, which is the optimal decision. So a 3% error in the mean is typical in while estimating while performing estimation tasks, right? So this kind of extreme sensitivity of solutions to perturbations has been disturbing. So there has been other approaches using robust optimization, distributionally robust optimization, etc. So this is the story from operations research or optimization under uncertainty side. So coming to an example in machine learning, here this is a popular figure many of you may have seen. Here we have an image of a panda, and we are talking about Google Net, which is known to have near to human classification performance. So if you present an image to the classifier, it will kind of perform near to human accuracy. So here you present an image of a panda, and with good confidence it says it's a panda. Now you add this small amount of adversarial perturbation. So this is the adversarial perturbation multiplied by a very small number. So I get again an image of a panda, really. So when humans look at it, we call it panda. But the machine, the machine, the Google Net machine, which calls it a gibbon with very high confidence. So this is one example. Modern machine learning, modern learning and decision problems tend to be over parameterized. And when talking about over parameterized problem, this quote classic by John von Neumann comes to mind. With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. It has actually been verified too. So there has been efforts to verify that too. So. So here we have an example, again continuing with examples in machine learning. So the problem that I mentioned, robustness to adversarial perturbations, when you present an adversarial, when you perturb your image slightly adversarially, the classifier gets thrown and it outputs grossly incorrect outputs. This has been observed across data sets and across classifiers. So this is known to generalize. So this is, for example, in the image classification, or here interestingly in the traffic signal. So you have a signal and you kind of have perturbed it with this love-hate image, which you find in traffic signals at times. So this is a camouflage gravity kind of perturbation, and it has been shown that you can fool the machine with around 67% confidence, around 67% of the time. And here is an interesting example where you have normal people like us. So when you add these special colored goggles, so these spectacles, the machine actually classifies them as celebrities. So so given that this is a state of an art algorithm, and it has these problems, we already have them employed in practice actually. You see arrest a man among a crowd of 60,000 concert goers. So there has been a lot of interest recently in both in machine learning, also in optimization under uncertainty, to actually give certified guarantees for adversarial robustness. So here I will be presenting a particular approach, a very recent approach called distributionally robust optimization from operations research literature. This is an extension of robust optimization idea, and I will be presenting this and its application to modern machine learning problems. So here, usual optimization problems will be of the form minimize over expected value of a loss. So you will be typically minimizing expected, in machine learning, you will be typically minimizing expected empirical loss. There you are asking for a decision which performs good against one probability distribution. Here instead, I am asking for a decision which performs good uniformly against a class of probability distributions. The class is a ball here, like really. Like, so I have my empirical distribution which is generated by the data, and I consider a ball of probability distributions around the data, and I ask for uniformly good performance against all these probability distributions. So this is what I'm asking. So not just, I want to find a decision which is not good against one probability distribution, but which performs uniformly good against all the probability distributions inside this ball. So this approach is what I call as distributionally robust optimization. Here you are really minimizing this worst case loss, and so you are guaranteeing a uniform performance against all these probability distributions. And in some sense, you are being distributionally robust. So this is the framework that we'll be considering. So here you need to define a distance between probability distributions, right? Like, so I mentioned, like, we are talking about putting a ball around probability distributions. So we need to specify a distance. So a natural way of specifying a distance, an extremely geometric and intuitive way, is what is called as optimal transport distances. Varun in his talk explained what they are. Like, I'll recollect again. So here we have two probability distributions, mu and nu. I need to define distance between these two probability distributions. So they have shapes. So I arrange the shape of the mu in the form of a sand pile and the shape of the nu in the form of a sinkhole. And I'm going to ask, what is the optimal cost? There is a cost. There is a cost for moving mass from point X to point Y, unit mass, and the cost is Cxy. I'm going to ask, what is the cheapest way in which you can transform this shape to fill this shape? Move the sand pile to fill this sinkhole. This is the question I'm asking. So the question can be directly posed as, find a map which minimizes which actually transforms this shape to this shape. This problem has been posed for around nearly 200 years, and it was known to be a very difficult problem, nonlinear problem. In around 1950s, an economist, Russian economist and mathematician Leonid Kontovich, he proposed a relaxation to solve this problem, which is, instead of looking at all deterministic maps, look at all randomized maps. That suddenly makes the problem a linear program. So here, instead of looking at all deterministic maps, he's asking for all possible couplings between two random variables with x and y, with x, the marginal distribution of x being mu and the marginal distribution of y being nu. What is the minimum cost? And this suddenly turns out to be a linear programming problem, which turns out to be tractable. So this is the distance we will be using. If in the particular instance of the transport cost being the Euclidean norm, we call it Wasserstein distance. So Wasserstein distance has been around known well in probability theory for several decades because they help analyze convergence of distributions. So Wasserstein distance are just a particular case of optimal transport distance. Okay. So just to give a better idea of what is happening. So when you put this Wasserstein ball around the probability distribution, what it does is essentially it perturbs the samples. So you are presented with data samples, and it perturbs the samples both in location and in magnitude, but within a budget constraint. So you are asking for robustness against these adversarial perturbations, and this is how you ensure robustness against adversarial perturbations by an amount which you choose. Okay. So just to make things concrete, let's take a very simple problem that we always resort to. If you want to pick an example problem, least squares regression. Yeah. So I take the least square regression problem where I want to fit a straight line. So the empirical risk minimization, which involves just minimizing the error in the data, can be given like this. So the corresponding distributional robust optimization problem, which I call as distributionally robust linear regression, is given like this. So you just, instead of minimizing against the empirical distribution, you minimize over all possible distributions uniformly within a ball. That's all. So interestingly, you may wonder, is this problem easy to solve? In our particular example, we kind of showed that this, exploiting a structure in the problem, this is actually indeed equal to minimizing mean square error plus a regularization, norm regularization term. So the distributionally robust linear regression problem actually turns out to be something which is well known and popularly adopted in practice called square root lasso. So this is only when I'm using a very specific Wasserstein distance. Yes. So when you use a Wasserstein distance, and you define this distributional robust optimization problem, it just turns out to be a square root lasso problem. So this in some way like kind of lends a little bit of credibility to the distributional robust optimization problem. These problems have been like known to be extremely successful and like popular like in practice for a decade or two now. So this lends a little bit of credibility to this in this direction. Okay. The same idea extends a little bit, and many other problems such as like logistic regression or support vector machines, quantile regression, least absolute deviation lasso, many of these regularization based algorithms actually can be represented equivalently as distributionally robust optimization with Wasserstein distances. So this in some way says norm regularization is good. It is useful. It provides a little bit of adversarial. There has been a plenty of interpretation of norm regularization. Here, like we kind of have the interpretation that like so they are also adversarially robust. Okay, good. So like last time, like when I gave a talk here, like probably I stopped at this point. Like so I gave a I explained these connections between like distributional robust optimization and machine learning algorithms. Now I'll probably just be explaining like what we have been doing new. Yeah. So one can ask like so all good, like for these simple problems it works well. But when I go to a tricky problem like an image classification problem in a neural network, is this actually working? At least very preliminary studies have shown that. So here like I have an image classification task where these dark ones, the first ones in the left are top left are original images, and in the subsequent like boxes what I have are perturbations. So and what I'm reporting is ERM just means empirical risk minimization. That's the naive thing that we would do. So if I adversarially perturb, what is the amount of adversarial noise that needs to be added so that it trips the classifier? The classifier gives the wrong output. So this is what I'm reporting here. So for ERM, when I adversarially perturb just this much, the output changes. On the other hand, when you actually like go to and there are many other like I report the output of many other like adversarial learning algorithms. Particularly for the Wasserstein case, actually like if you see this 3, if you look at this adversarial perturbation, it actually looks a little confusing. If we are presented with this, if 3 or 8, like it's not clear. And you can check that with many examples. Like so, what I'm trying to impart here is this principal method towards improving adversarial robustness has actually like kind of like at least like in preliminary examples seem to be working even in like difficult problems on large data sets. You can check that with like any image here. Okay. So okay, with the introduction, like after the completion of the introduction, like I'll just go on with discussing the structural and computational properties. One may even look at this and then say, is this problem even easy to solve? Like it looks like a crazy difficult problem. Even without this max, like I had enough difficulty. So with this max, like is it easy to solve? And like does it make it difficult or does it make it easy? Is the presence of this like adversarial robust adversary, does it make it easy or does it make it difficult? So we'll be looking at that in computational properties, and then we also look at asymptotic statistical properties. One particular like observation that I would like to register is like we actually can exploit the structure of this problem very beautifully, and then actually say that like even faster than empirical risk minimization, like the non-robust versions, one can design like faster algorithms, faster computational schemes. The second, actually like for a variety of problems, this approach appears to induce a loss-sensitive regularization. Usually we are familiar with norm regularization. Yeah. Yes. No, I'll be just reverting back to ER. Like so, when I mean like I get something better, I mean like putting delta greater than 0. So delta equal to 0 just like is going to be ERM because the only distribution in the ball is going to be just PN. Okay. So actually, what turns out here is like usually we adopt norm regularization. Instead, like what this adversarial robustness setting actually induces is a very specific loss-sensitive regularization. The loss-sensitive regularization is such that it actually like it minimizes your sensitivity to adversarial perturbations. I will show that in the results like that are coming. Thank you. Okay. So coming to structural properties, if I am presented with this problem, how would I like to solve it? Like what are the ways to solve it? First, like so I have this decision problem. I want to understand the inner max. So what I do is like I ignore the decision, like I ignore the minimizer over beta, I ignore the decision, like I look at the simple optimization problem here, just the inner maximization problem. How do I solve this? So this is like, as I just when I explained this topic, like I explained everything in terms of optimal mass transportation, right? Like so here at the end of the day, the probability distribution that attains this maximum will be, if you have a point x, it would have transported to some x plus delta x. So each point x, like in your original measure, in your original distribution, would have been transported to x plus delta x, where delta x solves this very local optimization problem. Okay, so this is the structure of the adversarial measure, which maximizes this which maximizes this inner supremum. So C is the transport cost. Like so, it's think of a Euclidean cost. C is the transport cost. So a point x gets moved to x plus delta x. So this is the adversarial perturbation, and delta x is not just a random x; it specifically solves this optimization problem. And if I want to represent this, I can represent it as a if I want to equivalently write this, a dual formulation, I'll just be exploiting LP duality, and I'll be able to write this in this nice form, where I just like have this inner optimization problem plus a budget constraint. Here the lambda is the Lagrange multiplier for this problem. So I have a budget constraint here. So lambda is just the Lagrange multiplier for this budget constraint. So like this LP structure in this optimal transport costs or Wasserstein distances allows easily to write these. Now given this, I had this without the decision variable. So I put back the decision variable, I get this simple, it's a nice expression. So what I can do with it is, for a specific example, let me look at specific examples. Let me look at the specific example of Euclidean norm. So I have the transport cost is just the Euclidean norm, just the Wasserstein distance case. So this is duality. So this is just the LP duality, but at infinite dimensions. Yes. So I have this transport cost, which is just the Euclidean norm. So I have a Euclidean norm sitting here. If you look at this particular function, it turns out to be a strongly convex. Here I have a C of x is a convex function, strongly convex function, and then I am taking the negative of it, so it's a strongly concave function. And if this is like convex or if this is convex, and if lambda is large, I can absorb this convexity here, and this whole thing will be strongly convex for large values of lambda. And when my budget constraint is small, it is typically the case that lambda will be large, so this inner optimization problem will be strongly convex. And I can solve this inner optimization typically in a gradient ascent, like we use 10 steps of gradient ascent, and I will be getting a nice solution for this inner optimization problem. And in particular examples such as like if you have linear decision rules, like so I'm looking at a very special case where you have linear decision rules. So the interaction between the randomness and beta is just L of beta transpose x. And in such particular special instances, it will only even take a univariate line search to solve the inner optimization problem. Not at all difficult. Yes. That is yes. So it will only take a univariate line search to solve such a problem. Like so, at the end of the day, what I'm trying to say is like solving this problem using a method like gradient descent or stochastic gradient descent is not very hard, because it takes only a univariate line search to compute the value at any point and its gradient. So this, if I can solve this inner optimization problem with something like a gradient descent or like univariate line search, then the whole thing is extremely easy, and it's not computationally difficult. Like scale of computation we have, it's not difficult at all. So at the end of the day, like this particular problem can be equivalently written as, if this is the original empirical risk minimization, naive empirical risk minimization problem I was having, this is the DRO version where I have similar structure. Like so, this is just a loss of beta transpose x. Like this is a slightly modified version of the loss. And I can employ, if I am using a stochastic gradient descent here, I can use stochastic gradient descent here too, right? So what turns out to be extremely interesting is, even if this problem is not strongly convex, let's say it's merely convex, it's not strongly convex, the distributional robust optimization problem actually turns out to be strongly convex. One can show, like by examining carefully the second derivatives, one can show that even if this original problem is not convex, not strongly convex, this turns out to be strongly convex. So, and you all know that like when I have strong convexity, methods like gradient descent, stochastic gradient descent perform really fast. So I can solve this robust problem much faster than the empirical risk minimization problem. I'm not presenting the expressions, like not. So here I am assuming that it's of the specific form and it is just merely convex. It's just merely convex. Yes, in a very specific context, like I want it to generalize, but it's much harder to go and show it actually. So in this very specific context, one can actually go and study the second derivative, the Hessian, and then prove that this is actually a strongly convex function in the, around the optimizer. Yes. So certainly that is certainly doable. I'm just like talking about solving this. What are the structural properties of this problem? So you will see that this strong convexity becomes easy even otherwise. Like so, it helps in like well conditioning the solution even otherwise. Yes. Yes. Yes, certainly. I can do that. There is no problem. So the DRO by itself has like the framework that I postulated itself has this adversarial robustness. Like that's the motivation behind it, not the computational properties. So I want to solve that problem, and I'm just saying that like it becomes extremely easy to solve, like with or without adding the certainly. Like I can always improve the condition number by adding an epsilon, and that has been being done by like for nearly 50 years now. Yeah, we can do that here too, but computation is not the reason why we are pursuing this. Like, I'm just saying, like, it turns out to be that like it is strongly convex here too. Okay, fine. Yes. 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 They are related, but this can be like, okay, so how do you determine what is the delta? It's a similar question to what we are putting here. Here do we have a delta? And this can be shown to be a slightly, so what you are saying is a traditional robust optimization formulation. And usually like the mainstream of robust optimization is to actually like choose your uncertainty over the whole support. But here like you are asking to put a delta, and it will be similar, and it can be shown to be a specific subcase of this. But actually like with this formulation, one can actually go and study like asymptotic properties, like what should be the rate at which this delta should be shrunk, which has not been like available in the respective robust optimization literature. But they are like, they intrinsically do similar things. Like this allows this has a little more power and flexibility, and it, yeah. So one can design stochastic gradient descent scheme that can solve this problem at least faster than the empirical risk minimization. So which is good. Like so, computation need not be a reason why one needs to deter away from such a setup. Okay. And then like coming to like whenever we try to understand the engineering system or like it's or an algorithm, it's often useful to like scale the system up and then study the asymptotic properties. So here too, like we have a specific algorithm, we have a formulation. So let's see what it does, like what it does. So I have this distributional robust optimization formulation that I have been talking. So the regime that I'm considering is I'm going to the field and collecting more and more samples. So I have more and more samples, and the number of samples is going to go to infinity. So does my accuracy improve? At what rate it improves, etc. So the radius of the ball has to be shrunk because like you are going and collecting more data, so your accuracy improves. So I am considering the regime where the radius of the ball is shrinking. Yes. The ball AL, does that become a nicer optimization? So if you make the ball KL, in fact that has been the first approach. Like the specific. Yes. The specific KL doesn't give significant computational advantages, but there is a relative called chi-square divergence, which gives reasonably good computational performance. But one disadvantage with this KL type of algorithms is like the support is constrained in KL. Like so, you are like all the other distributions inside the ball has to share the support of your empirical distribution, data distribution. So you really don't go and explore out of sample, which is the tricky thing. Also, in these examples, like we started with a norm, so you can like give information about the geometry of the problem here. So in all these ways, like this is a slightly more advantageous. Like we started with KL and we moved it here, we moved to this recently because it has these advantages. It allows you to explore out of sample, which is significant. Okay. So here, like just to understand the performance of the system, I'll be scaling the number of samples to infinity and I'll be shrinking the ball, the radius of the ball to 0. So the question is like, does it converge to the right optimizer and what is the rate at which it converges? Okay. To this end, we first show that this is the objective that I have been concerned about always. Like, so this is the objective. I have just written the objective for this specific like Euclidean norm cost function. If I can use just simple Taylor series expansion to show that it can be written as when the radius of the ball is shrinking to 0, it can be written as empirical risk plus some regularization plus something that can be ignored, like when compared to this regularization. Okay. So this is the empirical risk, which I always will be minimizing, and this is the extra regularization. And what is the form of this regularization? It is expected value of the gradient with respect to the x direction. So what does this function like? I have written S beta to just like kind of like show it as like sensitive. Yes, yeah. Yeah, PQR dual. Yeah. So here the Q and P here are the dual norms. Like yeah. So this S beta is just the expected value of the norm of the gradient. So the gradient in some way measures the sensitivity with respect to perturbations. Like so here it's important to note that the suffix here is x. The gradient is taken with respect to x. So when I move my samples, when I perturb my samples, how much does my loss change is measured by this gradient. And the norm of the gradient is a number which comes up with this. Right? So what this essentially does is it encourages the asymptotically speaking, it encourages you to choose decisions or optimizers which have low sensitivity measured by this S beta. Right? So for problems where norm regularization may not be natural, so here like this actually like you don't need to like one success of machine learning I would say has been like it has automated several things that we would be doing manually. Right? Like so here like I'm saying like there is a way it looks like I'm not making any tall claims. I'm just saying it looks like there is a way where we kind of like find the procedure itself finds the right regularizer for the given problem. If you have linear models, actually if you can see that the L prime of beta transpose X and the norm of beta will come out. So for linear problems, typically the norm regularization is typically good. But for problems where like for optimization problems where you don't have a linear dependence, this